Hello friends, you must have taken a break from part 1 of work, energy and power, and I would like to take you to part 2 of work, energy and power. Remember, this is solved past paper questions, and this is specifically AS Physics 9702, work, energy and power, and this is going to be part 2. Don't forget, you will find questions involving work done, power, kinetic energy, potential energy, elastic potential energy, gravitational potential energy, and a lot many more, including efficiency. So without wasting any time, let's go to part 2 of these solved past paper questions. I think in part 1 we stopped at this point here, and straight away I want us to continue to part 2. Part 2, an object falls vertically from rest through air. State and explain the energy conversions that occur as the object falls. It falls from rest. From a certain height, that means it initially had gravitational potential energy, which is going to decrease as it falls. And as it decreases, it is going to gain speed. That means it gains kinetic potential energy because the speed increases. And of course, if there is air resistance, it is falling through air, some of the energy, the loss in potential energy, also becomes an increase in the thermal energy, which is going to be due to the work done against the air resistance. Therefore, we shall say that the loss in potential energy, loss in potential energy, loss in potential energy due to decrease in height equals to the gain in kinetic energy equals the gain in kinetic energy due to increase in speed and or plus the increase in thermal energy due to work done against air resistance. Okay, so that is those are the energy changes which occur. The loss in potential energy, because there is a decrease in height, will become the gain in kinetic energy plus the increase in internal energy or thermal energy as a result of work done against resistance. A ball of mass 150 grams is thrown vertically upwards with an initial speed of 25 meters per second. Calculate the initial kinetic energy. So kinetic energy is equal to a half mv squared, which is simply going to be a half times the mass is 150 grams. 150 is 0.150 times the speed, which is 25 squared. Just check the calculator. 0.5 times 0.15 times 25 squared. So the kinetic energy is 46.8, which is approximately 47 joules. So I'll write 46. So this is 46.875, approximately 47 joules. Just a moment. Okay, sorry for that. It was just a power problem. So the ball reaches a height of 21 meters above the point of release. For the ball rising to the height, calculate the loss of energy of the ball due to air resistance. So it reaches a height of 21 meters above the point of release. Let's see the potential energy. The gain in potential energy is going to be mgh. So this is 0.15, that was the mass, times g, which is 9.81, times the height, which is 21. So we can check this. 0.15 times 9.81 times 21. That is 30.9. So this is 30.9. That is the gain in potential energy, but note that the kinetic energy was 47 joules. The initial kinetic energy was 47. It means not all of it has become potential energy. So we can get the difference. That is the loss. The loss equals to the kinetic energy minus the potential energy, which will be 46. It was initially 46.875 minus 30.9. 46.875 minus 30.9, which is 15.975, approximately 16. So energy loss is approximately 16 joules. Then the work done, the average force due to air resistance. So this is the work done. The loss in energy to air resistance is going to be the work done against air resistance, which is going to help us to find the average air resistance force. So the work done is equal to the loss in energy, which we have seen as 16 joules. So it means the resistive force, friction force, is going to be work done divided by distance. Work done is force times distance, so the resistive force is work done over distance, which is 16, and the distance moved was 21. So we check this, 16 divided by 21, which is 0.76. 0.76. So that is the average force due to air resistance. Determine the SI base units of power. Without wasting time, we know that power is the rate of doing work, or the rate of work done. So that is work done per unit time, which work done is going to be force times distance in the direction of the force, or displacement, then divide by time. So we substitute to find the units. So the units of power will therefore be force, which is kilogram meters per second squared, times distance, which is in meters, divided by time, which is seconds, and this simplifies to kilogram meters squared per second cubed. So kilogram meters squared per second cubed. The figure shows a turbine that is used to generate electrical power from the wind. The power P available from the wind is given by that expression. Show that C has no units. We must have seen this in physical quantities, but we shall still repeat it. So we begin by making C the subject. C is going to be equal to P divided by L squared rho V cubed. That is C. So we write the units. L is length in meters. Rho is density, that is kilogram per meters cubed. V is speed, which is in meters per second. And we have already the units for power, we have them above. So we shall just substitute now. So the units for C will be those of power that we have above, that were kilogram meters squared per second cubed, divided by L, which is meters but is squared, times density, which is kilogram per meters cubed, times V, which is meters cubed per second cubed. Meters cubed per second cubed, because it is raised to power 3. So we simplify this. In the numerator, I have kilogram meters squared per second cubed. I'm arranging the denominator. So I have kilograms meters squared times meters power -3 times meters power 3. I remain with the meters squared, then times s power -3. So we shall show the examiner that each term is cancelling out, and we shall conclude that C has no units. The length L of each blade of the turbine is 25 meters, the density is 1.3 in SI units, the constant C is 0.931, the efficiency of the turbine is 55%, and the electric power output is 3.5 times 10 power 5 watts. Calculate the wind power. So let's first of all find the power available from the wind, that is, which is going to be converted into electrical energy. The efficiency of the turbine is 55%, and the electrical power output P is 3.5 times 10 power 5 watts. So that is the output. Let's try to find the input. We know that efficiency is equal to the power output over the power input. So the efficiency is 55%, which is 55 over 100. The power output has been given as 3.5 times 10 power 5. Then the power input is not known, so we are going to find it. The power input is not known. So it means the power available from the wind that is converted into the power input, or the total power available from the wind, power available from wind is going to be the power input, which is going to be, I'm making power in the subject, so it will be 3.5 times 10 power 5. Multiply this by 100, divide by 55. I just got the reciprocal. So that is the power available from the wind, but only 55% of it becomes the output. So that is 3.5 exponent 5 times 100 divided by 55. So that is 6.36 times 10 power 5. From the calculator, 6.36 times 10 power 5 watts. That is the power available from the wind. So we can now find the wind speed using the expression given above. So we can now find the wind speed. I'm going to substitute in that expression, or make V cubed the subject. So V cubed is going to be the power available, which is 6.36 times 10 power 5. Power 6. It is power 5. Times 10 power 5 divided by, I'm making V cubed the subject in the formula above. They gave us V cubed is equal to P divided by C L squared times rho. So C L squared rho. So C is 0.931. L squared is 25.0 squared times the density, which is given as 1.30. So we press our calculator. That answer we divide by, open brackets, 0.931 times 25 squared times 1.3. Then we find the square root of the answer. The cube root, not square root. Cube root of the answer, and it is 9.4. So the wind speed is going to be 9.4. Here V is equal to 9.4 meters per second after finding the cube root. Suggest two reasons why the electrical power output of the turbine is less than the power available from the wind. Electrical power output is less than the power available from the wind. So number one, not all the kinetic energy of the wind is converted to kinetic energy of the blades. Some of it is wasted to overcome friction of the blades. That's number one. So not all the kinetic energy of wind is converted to kinetic energy of the blades. Some is wasted to overcome friction of the blades. So some kinetic energy is used to overcome the friction in the blades. It is wasted to overcome the friction in the blades. So not all of it becomes, not all of the kinetic energy of the wind becomes kinetic energy of the turbines. Number two, generator conversion. Of course, the generator may not be 100% efficient. So because it may end up producing some heat. So we can say generator conversion is not 100% efficient. Generator conversion to electrical energy. Generator conversion to electrical energy is not 100% efficient. Efficient as heat is produced in the generator. So some heat may be produced in the generator, meaning its conversion is not 100% efficient. Define power. We know power is work done per unit time. Work done per unit time or over time taken. Or you can say the rate of doing work. So that is power. Use your definition in Roman 1 to show that power may also be expressed as the product of force and velocity. Okay, so we have work done as force times displacement. Force times displacement in direction of force. That is work done. So it means power is going to be equal to force times the displacement divided by time. Hence, power is equal to force. Since change in displacement with the time is velocity, so power is equal to force times velocity. Power will be force times velocity. A lorry moves up a road that is inclined at 9.0 degrees to the horizontal as shown in the figure. The lorry has a mass of 2,500 kilograms and is traveling at a constant speed of 8.5 meters per second. The force due to the air resistance is negligible. Calculate the useful power from the engine to move the lorry up the road. The useful power from the engine to move the lorry up the road. Let's first find the force acting on this lorry up the plane. So if it has a mass of 2,500, that is mg, the force down the plane is going to be mg sine of 9.0, that is down the plane. is to be equal to the force up the plane because it's moving at a constant speed. mg sine 9.8. That is the force up the plane, down the plane, which is equal to the force up the plane. Okay, so and since it is moving at a constant velocity, then we shall say that power is equal to force times velocity. The force is going to be the force down the plane, which is mg sine 9.0, which is going to be 2500 times g, which is 9.81, times sine of 9.0. So that is the force down the plane, which is the same as the force up the plane because of the constant speed. So times the speed, which is 8.5. So let's check. 2500 times 9.81 sine of 9, then times 8.5. So that is 32.6, 32,610. 32,610 watts, which is approximately, since they want the answer in kilowatts, we divide by 1000, that is 32.6 kilowatts, which is approximately 33 kilowatts. State two reasons why the rate of change of potential energy of the lorry is equal to the power calculated in Roman 1. One, they said air resistance is negligible. It means there is no work done against air resistance. So that means the rate of change of potential energy of the lorry is equal to the power calculated. So number one, there is no work done. No work done against air resistance. Number two, they told us it was moving at a constant speed. That means there is no change in kinetic energy. So no change in kinetic energy at a constant speed. There is no gain or loss of kinetic energy. At a constant speed, no gain or loss of kinetic energy. Let me write this in full. No gain or loss of kinetic energy. If the speed is constant, there is no increase or decrease in kinetic energy. Explain what is meant by gravitational potential energy and kinetic energy. Of course, we know gravitational potential energy, that is the energy of a mass due to its position in a gravitational field. Energy of a mass. Energy of a mass due to its position in a gravitational field. Then kinetic energy, we know that energy of a mass due to its speed or due to its motion, that is kinetic energy. Energy of a mass due to its motion, or you can talk about its speed. That is kinetic energy. Okay, a ball of mass 400 grams, 400, I think that is 0.4 in kilograms, is thrown with an initial speed 30 at an angle of 45 degrees to the horizontal as shown here. Air resistance is negligible. The ball reaches a maximum height h after a time of 2.16 seconds. Calculate the initial kinetic energy of the ball, initial kinetic energy of the ball. So energy is going to be equal to a half m v squared. So this is going to be a half times the speed, which is, the mass, which is 0.4 times 30 squared. So a half is 0.5 times 0.4 times 30 squared. That is 180 joules. Then the maximum height h of the ball, the maximum height. Of course, we know at maximum height, velocity is 0, so we could use v squared equals to u squared plus 2as. At maximum height, v is 0. Initial velocity in the vertical, we are considering vertical motion. So it means we have to resolve v in the vertical. V in the vertical is going to be 30 sine of 45. V in the horizontal is going to be 30 cos of 45. So this is going to be 30 sine of 45 degrees. Because it is moving against gravity, acceleration will be negative 2 times 9.81, then times the height h. So this gives us h as 30 sine of 45 divided by 2 times 9.81. 30 sine 45 divided by 2 times 9.81. So that is 1 point. Is that true? Oh, this is squared. So I'll repeat this. 30 sine 45, but it is squared. This is squared divided by 2 times 9.81. Thirty sine 45 squared divided by, answer divided by open brackets 2 times 9.81. Okay, I hope that is true maybe. So that is 22.9. So this is 22.9. Another student would use S equals to UT plus a half AT squared. I'll use that one also. S equals to UT plus a half AT squared. So I am going to only consider when it is falling from the top. If it is falling from the top in the vertical, I'm considering vertical motion, but starting from the top. Where at the top, initial velocity in the vertical is 0 because it momentarily stops. So S is going to be equal to a half times 9.81 times the time. Do we have the time? The time is 2.16. Falling from the top because the ball reaches a maximum height h after time of 2.16. That means if it is falling from that height back, it will still take 2.16 seconds. So I will check that 0.5 times 9.81 times 2.16 squared. That is 22.9. Then the gravitational potential energy of the ball at height h. Gravitational potential energy at height h. So gravitational potential energy is going to be mg times h. The mass was 0.4 times g is 9.81 times h. We have seen h is 22.9. So let's press the calculator. 0.4 times 9.81 times 22.9. So that is 89.9. 89.9. I'll write 89.9. Is it inevitable to write 90? 89.9, that is fine. In joules, you can write 90. Then determine the kinetic energy of the ball at its maximum height. At its maximum height. So we have seen the potential energy of the ball at height h, and we have seen the initial kinetic energy, which was 180. That means not all the kinetic energy has become potential energy. There is a balance. So the balance is the kinetic energy at height h if air resistance is negligible. So kinetic energy at that height is going to be equal to the initial kinetic energy minus the gain in gravitational potential energy. So this means this will be 180 minus 89.9. So 180 minus the answer, that is 90.1. So this is 90.1, or approximately 90 in joules. Explain why the kinetic energy of the ball at maximum height is not zero. It can't be zero. At maximum height, it is the velocity in the vertical which reduces to zero, but the velocity in the horizontal remains constant. So even at the maximum height, the ball is still moving in the horizontal, although in the vertical it is no longer moving. Therefore, the kinetic energy cannot be zero. Reason: the horizontal velocity is not zero as the object is still moving. Horizontal velocity is not zero as the object is still moving. The object is still moving. It's only the vertical velocity that becomes zero. It's only the vertical velocity that becomes zero. Explain what is meant by work done. So we know work done is force times displacement in the direction of the force. Force times displacement in the direction of the force. That is work done. We have defined that enough. Okay. A boy on a board B slides down a slope as shown in the figure. Let's first think of what is happening here. Let's say the boy is here. We shall call this height h. Is sliding down, and state a word equation that links the work done by the force F on B to the changes in potential and kinetic energy. So when the boy is sliding, the work done is going to be equal to the decrease in gravitational potential energy minus the gain in kinetic energy, because as he's sliding, the potential energy decreases as the kinetic energy increases. So if there is no resistance, or if resistance is ignored, we shall simply say that the work done equals the decrease in gravitational potential energy, decrease in the gravitational potential energy, minus the gain in the kinetic energy. So if the resistive force F, of course F opposes a sliding downwards. So if not all the decrease in gravitational potential energy becomes kinetic energy, it means the difference between the gravitational potential energy and the kinetic energy, the gain in kinetic energy, is the work done against the resistive force F. That is the word equation, minus, this is minus. The boy on the board moves with velocity v down the slope. The variation with the time t of v is shown in the figure. So they have given us a graph of v against time. Total mass of B is 75 kilograms. For B from t equals to 0, t equals 2.5. Let's look for t equals 2.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I hope that is 2.5. So 2.5 is against the scale on the vertical is 2 divided by 10, which is 0.2. So I think this is 7. I think that is 7.4. 7.4. 0.6, 0.8, then 8, 7.4 on the vertical. Show that the distance moved down the slope is 9.3. So they're telling us to show that the distance, this distance here is 9.3. This 9.3 in meters. So let's find that distance. So that distance is actually equal to the area under that line. So distance equals to the area under the line. So the area on the vertical, we have seen that is 7.4. On the x-axis, it is 2.5. So this is going to be a half times 7.4 times 2.5. A half is 0.5 times 7.4 times 2.5, which gives us 9.25. That is approximately 9.3 meters. Calculate the gain in kinetic energy. Gain in kinetic energy. So we know kinetic energy is equal to a half m v squared. So this is going to be equal to a half times the mass, I think, is 75, times the speed, the speed at 2.5 is 7.4, so this is going to be 7.4 squared. Because initially the speed is 0, so the initial kinetic energy is 0, then now the final kinetic energy is this, so the gain is just the final kinetic energy, which is going to be equal to a half is 0.5 times 75 times 7.4 squared, which gives us 2053 or 2054. 2054, that is approximately 2100 joules. Then calculate the loss in potential energy. Loss in potential energy. Energy in the vertical must be mgh. Potential energy is in the vertical. So we need to find h. Go back to the diagram and look for h. h is the vertical height. We have this as 30. This is 9.3. So opposite hypotenuse, that is sine. So sine of 30 is equal to the opposite, which is h, over 9.3, which means that our vertical height is 9.3 sine of 30. So h is 9.3 sine 30. We just use that one. So we are now substituting. So we have seen that h is 9.3 sine of 30. So the loss in potential energy is going to be mass, which is 75 times 9.81 times 9.3 sine of 30. So we check this. 75 times 9.81 times 9.3 sine of 30. So that is 3421, which is approximately 3400. 3421 joules, which is 3400 joules. Then calculate the resistive force. We have seen the gain in kinetic energy is not equal to the loss in potential energy. The gain in kinetic energy is not equal to the loss in potential energy. It means some work is done against resistance. So work done against F must be equal to 3400 minus 2100. And this is approximately 3400, 2100. That is 1300. So the resistive, remember, work done is force times distance. So the resistive force F is going to be the work done divided by the distance, which is 9.3. So that is divided by 9.3, which is 130. Is it 139? That is too small. Let me check. Let me use more original values. I'll not use this. Let me check these values. I change them to more exact values. It is very dangerous to use rounded off values on the next steps of the question. So that is 3421 minus 2054. Let me use that one. 3421 minus 2054. So that is 1367. 1367 joules. So let me use 1367. 1367. 1367 divided by 9.3. So that is 146.999, which is approximately 150 in joules, newtons. Approximately 150 newtons. So that is the resistive force F. Approximately 150 in newtons. Define power. We know power is the rate of doing work. Rate of doing work. Work done per time. Work done over time taken, that is power. The figure shows a car traveling at a speed of 22 meters per second on a horizontal surface. The car has that mass 1,500, a resistive force 1,200 newtons acts on the car. Calculate the force F required from the car to produce an acceleration of 0.82. So we want the force F on the car. which is required to produce that acceleration. So let's call this force, okay, I'm going to call it FD, forward the driving force. The resultant force is the one which gives that acceleration, and the resultant force, okay, they call the force required is F. Let me call this F, then the other one I'll call it FR to mean resultant. So since they called that one F, the resultant force Fr is going to be the forward force F minus the resistive force. The resultant force is given by mass times acceleration is going to be equal to the force F minus the resistive force, which is 1,200. So they have given us the acceleration. So it means F is going to be the mass, which is 1,500, times the acceleration, which is 0.82, plus, I'm taking this one the other side, plus 1,200. 1,500 times 0.82 plus 1,200, which is 2,430. So this force is 2,430. I'll write here 2,430 newtons. Then the power required to produce this acceleration. So now power is easy. Power is force times velocity, which is equal to the force is 2,430 times the speed, which is 22. So the answer times 22, that gives us 53460. 53460 watts. Then the resistive force on the car is proportional to V squared, where V is the speed of the car. Suggest why the car has a maximum speed. The resistive force is proportional to V squared. Suggest why the car has a maximum speed. Of course, we know that the resistive force, when how should I make it? First of all, there is a maximum power from the car, and when the resistive force is equal to the force produced by the car, there will be no acceleration. That means at this point, the speed will become constant. So one, there is a maximum power from the car. The car does not produce power indefinitely. So there is a maximum power. There is a maximum power from the car. There is a maximum power from the car, and when the resistive force equals the force produced by the car, when resistive force is equal to the force produced by the car, there will be no acceleration. There will be no acceleration when the resistive force is balancing with when the resistive force balances with the force produced by the car, there will be no acceleration because the resultant force is zero. That means the speed must remain constant, hence maximum speed. So when the resultant force, when the force produced by the car is equal to the resistive force, then it means there's no resultant force. Therefore, the acceleration will be zero, and that means the speed cannot increase any further. That will be the maximum. Define acceleration. We know that acceleration is the rate of change of velocity, or change in velocity with time. Rate of change of velocity. That is acceleration. Rate of change of velocity. That is acceleration. It is not a velocity over time. The velocity must be changing. Also, you can say acceleration is equal to change in velocity divided by time taken. A man travels on a toboggan down a slope covered with snow from point A to point B and then to point C. The path is illustrated there. We can look at the path. So before we go any further, since we can even find the height h with that horizontal, this is h, and if we know the distance between A and B, we shall be able to find h. Secondly, we need to be able to resolve along the plane and perpendicular to the plane where necessary. Let us see the questions first. So the slope AB makes an angle of 40 degrees with the horizontal, and the slope BC makes an angle of 20 degrees with the horizontal. Friction is not negligible. That means there is friction here. The man and the toboggan have a combined mass of 95 kilograms. The man starts from rest at A and has a constant acceleration between A and B. The man takes 19 seconds to reach B. His speed is 36 meters per second at B. 19 seconds to reach B. Speed is 36 meters per second at point B. And the man starts from rest. So equations of motion, if the acceleration is uniform, then we can find the acceleration here. So using v equals to u plus at, since we have the time. So v at B is 36, v at A is 0 because started from rest, plus the acceleration A times the time, which is 19. So I'll just divide both sides by 19. So acceleration is going to be 36 over 19. 36 divided by 19, that is 1.89. So this is 1.89 meters per second. 1.89 meters per second. Show that the distance moved from A to B is 340. So we are having that this distance here is 340 meters. Okay, let's verify. So using the equations of motion, we want distance from A to B. So I'll use S is equal to ut plus a half at squared. I'm now substituting. Initial velocity is 0. It started from rest, so that's this part will be 0. I remain with a half times the acceleration I've got as 1.89. The time it is taking is 19 seconds. So it is 19 squared. So I'll have 0.5 times 1.89, then times 19 squared. That is 341. So this is 341, which is approximately 340 meters. For the man and the toboggan moving from A to B, calculate the change in kinetic energy. At A is at rest, at B is moving with the speed, so the change in kinetic energy is due to that only at B. So kinetic energy is equal to a half mv squared. So the change in kinetic energy, because at A kinetic energy is 0, I'll just consider that B, which is 9.5, times the mass, which is 95, times the speed, which is 36 squared. 0.5 times 95 times 36 squared. So that is 61560. 61560, or approximately 2000 joules. Then the change in potential energy. Change in potential energy. Remember, we are looking at A and B. That means we need now the height h. So the change in potential energy, is equal to mg times the change in the value of h. And we have seen from the diagram that we can find h. If this is 340, this is opposite, this is hypotenuse. So that is sine. Sine of 40 is equal to the opposite over hypotenuse, which is 340. So h is 340 sine of 40. So we now find that. So I'm substituting. This will be equal to m, which is 95, times g, which is 9.81, times h, which is 340 sine of 40. So we have 95 times 9.81 times 340 sine of 40. So that is 203,000. 203,670. I'll just write 676 joules. Approximate it can be 204,000 or 200,000, but I'll use this for further calculation. Use your answer in Roman 2 to determine the average frictional force that acts on the toboggan between A and B. We have seen the change in the gravitational potential energy is not the same as the change in kinetic energy. That means some work is done against friction. What is that work done? So work done against friction must be equal to 203,676 minus, I will also use the other one, which is 61560. 203,676 minus 61560. So that is 142,116 joules. That is the work done against friction. And we want to find the frictional force. So the frictional force, because work done is equal to force times distance. So the frictional force is going to be the work done, which is 142,116 divided by the distance, which is 340. So that one divided by 340. So that is 417.99. 417.99, which is approximately 420. That is approximately 420 in joules. A parachute opens on the toboggan as it passes point B. There is a constant deceleration of 3.0 meters per second squared from B to C. Calculate the frictional force that produces this deceleration. Because there is a constant deceleration, the frictional force upwards must be greater than the force downwards. So let's go back to the diagram. So there is a constant frictional force upwards, which is causing a deceleration. That means the resultant force is in the opposite direction. So the resultant force will be negative, or the acceleration is negative. But there is a force down the plane, which if we consider the object somewhere here, the force down the plane will be equal to the weight, which is mg, that is down the plane, mg sine of 20 degrees, that is down the plane. Then there is a resistive force up the plane. The resultant is responsible for the deceleration. So the resultant force F is equal to mass times acceleration, which is going to be the mass. Okay, so this will be equal to the difference between the two forces. So I will say this is the force downwards is mg sine 20 minus the frictional force. Alternatively, I would say the frictional force minus mg sine 20 because it is slowing down. But now, if I don't do that, I know the acceleration is negative, so I'm substituting. So the mass is 95. The acceleration is negative 3.0 because it is a deceleration. The mass is 95 times 9.81 sine of 20 minus the frictional force. So I just solve for the frictional force. So I have 95 times negative 3, which is that, minus, I bring the other one the other side, open bracket, 95 times 9.81 sine of 20. So the answer is around negative 603.7 is equal to negative FR. That means FR is 303.7 or 0.4. So FR is approximately 604 or strictly 600 in newtons. Explain what is meant by gravitational potential energy and kinetic energy. I hope we have answered such a question. The energy of a mass due to its position in a gravitational field is the gravitational potential energy. Energy of a mass due to its position in a gravitational field. Then kinetic energy, that is the energy of a mass or energy mass has due to its speed. Energy a mass has due to its speed. Energy a mass has due to its speed or due to its motion, that is the kinetic energy. A motion sensor is used to measure the velocity of a ball falling vertical towards the ground, as shown here. The ball passes through a point A and B as it falls. The ball has a mass. The mass is 1.5. The variation with the time of the velocity is shown here. So this is v against time. That is v against time. Let's check where it starts from here. I think the scale here is 4 minus 3 over 10, that is 0.1. So this is 3.9. Let's check here. And I think that is 7.8. Then here it is at so here it is at 0.8. Okay, let's now see the questions. Use the figure to calculate for the ball falling from A to B the displacement. So the graph was showing the speed from A to B. Now we want to find the displacement, so we can use equations of motion. The easiest I think is S equals to a half into U plus V times T, because we want to find a displacement. So we can say that S is equal to a half. We have seen that U from the graph is 3.9 and V from the graph is 7.8. Then the time between is 0.8. No, it is from 4 seconds, 0.4 seconds to 0.8. The difference is 0.4. So this will be times 0.4. And that gives us 0.5 times open bracket 3.9 plus 7.8 times 0.4 that is 2.34. 2.34. I hope we could also find the acceleration and use any other method. We can use, alternatively, acceleration is equal to the gradient, which is 7.8 minus 3.9 divided by 0.8 minus 0.4 from the graph. So open bracket, 7.8 minus 3.9 divide by, open another one, 0.8 minus 0.4. So that is 9.75. 9.75, that is the acceleration, 9.75. So the acceleration is 9.75. That means we can use now any other equation which has acceleration. For example, s is equal to u plus at, v squared equals to u squared plus 2as. Let me use one of those, v squared equals to u squared plus 2as. So v squared, this is 7.8 squared, mine equals to 3.9 squared plus 2 times a, which is 9.75 times s. So let's check. 7.8, that is squared, minus 3.9, that is also squared. Get that one, divide by, open brackets, 2 times 9.81, and that is 2.33. So this one will give s as 2.33 approximately. You can also check with s equals to ut plus a half at squared. It will give you approximately the same value. Or you can use s equals to ut plus a half at squared. As long as you have the acceleration, the methods have now increased. Okay, the second part wants us to find the acceleration, and since I've already found it, I'll just write it here. Acceleration is equal to change in velocity v minus u over t, which is the same as the gradient. The gradient of the line, which is 7.8 minus 3.9 divided by 0.8 minus 0.4, which we got as 9.8 or 9.75. Then the change in kinetic energy, we know that kinetic energy EK is a half mv squared. Now we want the change. Remember the speed changes, so this will be a half times the mass. Okay, let me write the final speed v squared minus a half initial speed, so that will be u squared, so that people will see that I'm doing a half times the mass, which is 1.5 times 7.8 squared minus a half times 1.5 times 3.9 squared. That is the change in kinetic energy, which is the same as, I'll just say 0.5 times 1.5 times, open brackets, I'll simply say 7.8 squared minus 3.9 squared. So that is 34.22, approximately 34. Show that the work done by the gravitational field on the ball in B as it moves from A to B is equal to the change in kinetic energy. Let's find the work done. We already have the change in kinetic energy. So work done is equal to force times distance moved. This is going to be the force. The force is going to be the weight, which is mg, times the distance moved. I'm now substituting. The mass is 1.5. Then g is 9.81. And the distance moved, we have seen it above, it was 2.34. The distance moved, was it? Yes. The displacement was 2.34, so that is 2.34. So let's press our calculator. 1.5 times 9.81 times 2.34. So we are getting 34.4, which is approximately 34. And this is equal to the change in kinetic energy, which is equal to the change in kinetic energy that we have seen above. State what is meant by work done. We know that work done is force times displacement in the direction of the force. Force times displacement in the direction of the force. A driver releases a solid sphere of radius 16 centimeters from the seabed. The sphere moves vertically upwards towards the surface of the sea. The weight of the sphere is 20 newtons. The upthrust acting on the sphere is 170 newtons. The upthrust remains constant as the sphere moves upwards. Calculate the density of the sphere. First of all, we know density is mass over volume. And we know that the mass will be equal to the weight. Since they gave us weight, that will be weight over g. And also, we know that the volume, because it's a sphere, volume of a sphere is 4 over 3 pi r cubed. 4 over 3 pi r cubed. So let's now find the density. Density will be equal to the mass, which mass is weight over gravity, so that is 20 divided by 9.81 divided by the volume, which volume is 4 over 3 pi, where there is the radius was given as the radius is 16 centimeters, which is 0.16. So this will be times 0.16, and this is cubed. So I'm just going to press the calculator and divide. So 20 divided by 9.81. Then, of course, I will get the reciprocal here. So I'll say times 3. And I divide by 4 pi times 0.16 cubed. So I'm getting 118.8, which is approximately 120. So this is 120. By briefly explain the origin of the upthrust acting on the sphere. Of course, upthrust is as a result of difference in the pressure between the top and bottom of the object when it is submerged. So the pressure at the lower surface is actually greater than the pressure at the upper surface, since pressure increases with depth. So we can say the pressure on the lower surface of the sphere is greater than the pressure on the upper surface. So the difference in pressure is going to be the upthrust. So upthrust is area times difference in pressure. That is the upthrust force. difference in pressure at the top and bottom of the object. Then calculate the acceleration of the sphere as it is released from rest. Acceleration. Let's find the acceleration as the resultant force over the mass. What is the resultant force? The weight is 20 newtons downwards. There's an upthrust force 170 newtons upwards. So there is a resultant force, which is 170 minus 20. 170 minus 20 divided by the mass. The mass is weight 20 over g, which is 9.81. So we have 170 minus 20, I think that is 150. So 150 divided by, open brackets, 20 over 9.81. So that is 73.57, which is approximately 74. The viscous drag force D acting on the sphere is given by that expression, where r is the radius of the sphere and v is its speed. The constant k is equal to 810 kilograms per meters cubed. Determine the constant terminal speed reached by the sphere. So think of the sphere falling in a liquid. Its weight is acting downwards. Actually, it is the sphere, I think, is raising upwards. A diver releases a solid sphere at the seabed, so it is raising upwards. Motion is upwards. So if motion is upwards, I'll use this for motion. It means viscous drag is downwards. That is, friction in the liquid is downwards. But of course, upthrust is upwards. Viscous drag is downwards, upthrust is upwards. So it means the weight plus the drag, if it reaches a constant speed, the weight plus the drag should be equal to the upthrust. And if that is true, the weight is 20, the drag is d, and the upthrust is 170. So it means the drag is going to be 170 minus 20, which is equal to 150. So the drag force is 150 newtons. Let's now substitute here. So 150 is going to be equal to k. K is 810 times r. Radius was 16 centimeters, so that is 0.16 squared. Then times v squared. So I'll just find v from 150 divided by, open brackets, 810 times 0.16 squared. So that is 7, or I have again to find the square root. So I'll get the square root of the answer, which is 2.69. So v is equal to 2.69, or approximately 2.7. The diver releases a different sphere that moves with a constant speed of 6.3 meters per second directed towards a stationary ship. The sphere emits sound of frequency, that is the normal frequency, this is Fs. The ship detects sound of frequency, so this is F observed, as the sphere moves towards it, so it is towards. Determine to 3 significant figures the speed of the sound in the water. So the observed frequency is equal to V times Fs divided by V minus Us. We saw this in waves. So the observed frequencies, the reason as why I have a minus is because it is towards, the frequency is higher. If it was away, the frequency is lower, this would be plus. So 4870 is equal to V times 4850 divided by V minus the speed of the source, which is 6.30. So we solve this. We are solving this. 4870 into brackets V minus 6.30 should be equal to 4850 times V. So you can open 4,870 minus 4,850 into brackets V. I'm collecting like terms. Should be equal to the other side. I'm taking 4,870 times 6.30. You can solve this in any way you want. So I press my calculator. 4,870 times 6.3 divided by both sides. I have 4,870 minus 4,850. So that is 1534. So V is 1534, approximately 1530 meters per second. Explain what is meant by work done. So work done is force times displacement in the direction of the force. Force times displacement in the direction of the force. A ball of mass 0.4 kilograms is dropped. That means initial velocity is 0. The ball falls from rest through a vertical distance of 70-80 meters to the ground. Air resistance is significant so that the ball reaches a constant terminal velocity before hitting the ground. The ball hits the ground with a speed of 23 meters per second. Calculate for the ball falling from the top of the building to the ground the decrease in gravitational potential energy. So decrease in gravitational potential energy is equal to mg, change in height. We substitute mass 0.42, g is 9.81, then times the change in height. It is falling through 70-80 meters, so that is times 70-80. So 0.42 times 9.81 times 78. That is 321. 321, which is approximately 320 joules. Increase in kinetic energy. We know that kinetic energy is equal to a half mv squared. Because it is just dropped, the increase in kinetic energy is simply going to be the kinetic energy with which it lands. So that will be a half times the mass, which is 0.42, times its speed, which is 23 squared. So that is a half times 0.42 times 23 squared. So that is 11109, which is approximately 110 in joules. Use your answers in B to determine the average resistive force acting on the ball as it falls from the top of the building to the ground. We have seen that the increase in kinetic energy is not the same as the decrease in gravitational potential energy, so that means there is work done against resistance. And this work done against resistance is going to be 320 minus 110, which is, I think that is 210 joules. That is 210 joules. That's the work done against resistance. But remember, work done is force times distance. So it means the resistive force, which I call F resistive, is going to be the work done, which is 210, divided by the distance, which is 78, because it moves through 78 meters. So we have 210 divided by 78. That is 2.69, which is approximately 2.7. The ball is dropped at time t equals to 0 and hits the ground at time t equals to capital T. The acceleration of free fall is g. So it means initially when it is dropped, before it is dropped, initial acceleration is g. But as it is dropped, because the air resistance increases in the opposite direction, it means the acceleration actually is going to decrease. But the speed is increasing. The speed is increasing until it hits the ground at time t equals to t, but the ball is reaching terminal velocity before hitting the ground. It reaches terminal velocity before it hits the ground. That means our graph is going to touch the x-axis before we reach capital T. So the acceleration is decreasing, but the decrease reduces as the resultant force becomes smaller. So it means this is going to be a curve which has a decreasing gradient, but touches the x-axis before reaching point T. So it is going to be a curve, can increase the thickness. It is going to be a curve. It should be a smooth curve, which touches the x-axis before time t, because the ball reaches terminal velocity. In other words, acceleration becomes 0 before it hits the ground. At t equals to capital T, it hits the ground. That means it hits the ground when it has already reached terminal velocity. So the graph touches the x-axis before reaching capital T. And the line is curved with a gradient that becomes less negative. In other words, the gradient becomes smaller in magnitude. That is less negative. Okay, I will reduce the thickness again. Explain what is meant by the concept of work. We have already seen that work is force times displacement in the direction of the force. Force times displacement in the direction of the force. Use your answer to A, derive expression for the increase in gravitational potential energy, delta EP, when an object of mass m is raised vertically through a distance delta h. So since work done is force times displacement, what is the force? The force is going to be equal to the weight of the object, which is going to be m times g. That means now the work done is going to be equal to the change in gravitational potential energy, which is equal to the force, that is mg, times the distance, which is h. Hence, it is simply mg change in h. The spring hangs vertically from the fixed point, and a mass of 94 grams is suspended from the spring, stretching the spring as shown here. So the mass is raised vertically so that the length of the spring is its unextended length. This is illustrated in figure 5.2. The mass is then released. The mass moves through a vertical distance of 2.6 centimeters before temporarily coming to rest. And this position is shown in figure 5.3. State which diagram, 5.1 or 5.2 or 5.3, illustrates the position of the mass such that the mass has maximum gravitational potential energy. So for maximum gravitational potential energy, it should be at its highest point. That means it is going to be figure 5.2, because it is in 5.2 where it is at its highest point. Then the spring has maximum strain energy. That is when it is stretched fully. So strain energy is stored when the material is stretched, so that is going to be in position in figure 5.3. Figure 5.3, because it has the greatest extension. Briefly describe the variation of the kinetic energy of the mass as the mass falls from its highest position to its lowest position. At the highest position, kinetic energy, it is falling. From the highest position, kinetic energy increases from 0 at the highest point, then it becomes maximum when it is passing equilibrium, and then decreases to 0 at the lowest point. So kinetic energy increases from 0 at the highest point. And then decreases to 0 at the lowest point. So if this is the highest point and this is the lowest point, it starts from rest. When it is falling, kinetic energy increases to equilibrium, then it starts decreasing to the lowest point because it's now moving against, against the restoring force. So when it is falling downwards, kinetic energy is increasing up to equilibrium. Then when it passes equilibrium, it decreases. We saw that in A-level simple harmonic motion. The strain energy E stored in the spring is given by this expression, where K is the spring constant and X is the extension of the spring. For the mass moving between the positions, figure 5.2 and 5.3, where the extension is 2.6 centimeters, calculate the change in the gravitational potential energy. So the change in the gravitational potential energy is going to be mg times the difference in height. The mass was given as, I think, 90. What was the mass? Is it 94 grams? So the mass is 94 grams. So that is 94 times 10 power negative 3 times g, which is 9.81, then times the height h, the change in height, which is 22.6 centimeters. So that is 2.6 times 10 power negative 2. 94 exponent negative 3 times 9.81 times 2.6 exponent negative 2. So that is 0.024. The change is 0.024. Determine the extension of the spring at which the strain energy is half its maximum. Strain energy is half its maximum. We have strain energy E is equal to a half kx squared. Strain energy is equal to a half kx squared when the extension is x. Now, at half of its maximum, so let this be the maximum, let it be x naught, okay. Let this be x naught. Then at half its maximum, determine the extension of the spring at which the strain energy is half its maximum value. So if this is the maximum value, then half of this, a half times k times the distance squared is equal to a half of a half kx naught squared, because the kinetic energy is going to be half of its maximum. The elastic strain energy is half its maximum value. So half cancels, and I think k cancels. So it means d squared is equal to x naught squared, I think, over 2. So this means D is going to be equal to x naught over the root of 2. The maximum was at 2.6. So this is going to be 2.6 divided by root of 2, which is equal to 2.6 divided by root of 2. That is 1.84. So this is 1.84 centimeters. So I just use the simple relations here. You can also use the first value of kinetic energy, a half k. X squared was 0.024 when it was x. Then the next one is going to be a half k times d squared is going to be equal to half of this maximum. So this is 0.012. So remember, this is 2.6. You combine the two equations, you're going to get 1.84. But me, I use the simple relations. Distinguish between gravitational potential energy and electric potential energy. So what is the difference? Electric potential energy is stored when charge is moved due to the work done in the electric field. The electric potential energy is stored when charge is moved due to work done in an electric field. That is for electric potential energy. It is stored when charge is moved due to work done in an electric field. Then for gravitational potential energy is stored when a mass is moved due to work done in a gravitational field, So that is the difference. For gravitational potential energy, it is a mass which is moved due to work done in a gravitational field. For electric potential energy, it is a charge due to work done in an electric field. A body mass m moves vertically through a distance h near the Earth's surface. Use the defining equation of work done to derive an expression for the gravitational potential energy. So we know that work done is equal to force times displacement in the direction of force. And of course, the force is going to be the weight. The force is going to be the weight, which is going to be m times g. That is the force. So it means the gravitational potential energy is going to be the force, which is mg, times the height h. That is mgh. Water flows down the stream. Water flows down a stream from a reservoir and then causes a water wheel to rotate. It causes a water wheel to rotate as shown here, so we can see what is happening. As the water falls through a vertical height of 120 meters, gravitational potential energy is converted to different forms of energy, including kinetic energy of the water. At the water wheel, a kinetic energy of the water is only 10% of its gravitational potential energy. That means the gravitational potential energy, only 10% is converted to kinetic energy. Show that the speed of the water as it reaches the wheel is 15 meters per second. So we know that potential energy is mgh, and kinetic energy is equal to a half mv squared. So only 10% of the gravitational potential energy becomes kinetic energy. So I will say 10% of mgh is equal to kinetic energy, which is a half mv squared. So m cancels out. So 10% is 0.1, so I will say 0.1 times g, which is 9.81 times h, which is 120, is equal to a half times v squared. So we can check this. 0.1 times 9.81 times 120, multiply this by 2, and we find the square root. That is 15.3. So V is 15.34, which is approximately 15. The rotating water wheel is used to produce 110 kilowatt of electrical power. Calculate the mass of water flowing per second through the wheel, assuming that the production of electrical energy from kinetic energy of the water is 25% efficient. Only 25 of kinetic energy becomes electrical power. That's what it means. Only 25 of kinetic energy becomes or is converted to electrical energy. So it means the energy which is converted is 25% of kinetic energy. So electrical energy is going to be equal to, let me say, electrical energy is equal to 25%. That is 25 over 100 times the kinetic energy, which is a half, times the mass, times v squared, which v is 15.3. So times 15.3 squared. That is the electrical energy. But remember, electrical power is electrical energy divided by time. So it means this is going to be equal to electrical energy, which is 25 over 100 times a half m. I will divide m by t because of this t here. Then times 15.3 squared. I've divided m by t because I want mass per second. But in other words, I'm dividing electrical energy by time. So the power is given as 110 kilowatts. So I will say that 110 times 10 power 3 is equal to 25 times 15.3 squared divided by 100 times 2 times mass over time. So we find mass over time, or we make m over t the subject. M over t is going to be equal to 110,000 times 100 times 2 divided by 25 times 15.3 squared. So 110,000 times 100 times 2 divided by 25 times 15.3 squared. So that is 3759. So this is 3759 kilogram per second, or 3750. I mean 60. 3760 to three significant figures. 3760 to three significant figures. You can also verify that. Define force. We shall say unit called force, density, and pressure, but force is the rate of change of momentum. Rate of change of momentum. That is force. Rate of change of momentum. Then a work done, that is force times displacement in the direction of the force. Force times displacement in the direction of the force. The force F acts on a mass m along a straight line for a distance s. The acceleration of the mass is a, and the speed from an initial speed changes from u to final speed v. State the work W done by F. So we know work done is force times distance. You can, since force is mass times acceleration, you can say ma times s. Since you can go further and simplify that, but they didn't tell us in which terms. So I can say F times s or ma times s. Use your answer in Roman 1 and an equation of motion to show that kinetic energy is equal to that. So in Roman 1, I have that work done is equal to ma times s. And I will use an equation which is v squared equals to u squared plus 2as. From this equation, I make as the subject. So as is equal to v squared minus u squared divided by 2. So I substitute for work. So this implies that work is equal to the mass into v squared minus u squared over 2, which is simply a half times m times v squared for u equals to 0. So if it starts from rest, initial velocity is 0. So it means for u equals to 0, the work done is equal to that. So it means kinetic energy is equal to a half m v squared. That is for initial velocity equals to 0. A resultant force of 3,800 newtons causes a car of mass 1,500 kilograms to accelerate from an initial speed of 15 to 30. Calculate the distance moved by the car during this acceleration. So 3,800 is the resultant force. So work done can be got from change in kinetic energy. Work done can be obtained from the change in kinetic energy, which is a half. Of course, the kinetic energy is above, the formula is above, so a half times 1,500. Final kinetic energy speed is 30 squared. Initial speed is 15. I will square it because it is a half mv squared. So I get the work done here. 0.5 times 1,500 times, open brackets, 30 squared minus 15 squared. So this is 506,250. 506,250 joules. That is the work done. Then let's find the distance. We know that distance is equal to the work done divided by the force. So this is going to be 56,250 divided by the force, which is 3,800. So let us see, divide by 3800. That is 133. So that is 133. Since we have resultant force, you could also use it to find the acceleration and use the equation of motion. That is, I could use the resultant force to find the acceleration from resultant force, which is 3,800 over the mass, which is 1,500. That is the resultant, that is the acceleration. 3,800 divided by 1,500, that is 2.53. 2.53 meters per second squared, that is acceleration. So you can use an equation of motion such as v squared equals to u squared plus 2as, with v being 30 squared, u being 15 squared, plus 2 times a, which is 2.53, then times s. This should be able to give you s as 133 meters approximately. The same force is used to change the speed of the car from 30 to 45. Explain why the distance moved is not the same as that calculated in 1. Now the speed is changing from 30 to 45, so the work done is not the same since the change in kinetic energy is different. From 30 to 40, the work done is not going to be the same because the change in kinetic energy is different. Note that we don't find kinetic energy by subtracting 45 minus 30 or 30 minus 15. It is 45 squared minus 30 squared. The other one was 30 squared minus 15 squared, and I don't think these are the same values. You can check. 45 squared minus 30 squared. That's what you get. 30 squared minus 15 squared. You get a different value. So it means the change in kinetic energy is not the same. So the work done is not the same. So the change in kinetic energy is greater. In this case, the change in kinetic energy is greater. So the work done by the force has to be greater. And if the work done is greater, since work done is directly proportional to distance, hence distance must be greater. Hence distance must be greater for the same force. The change in kinetic energy is greater when the speed changes from 30 to 45 by the force. So the work done by the force has to be greater, hence distance must be greater for the same force. Define the term power. Terms power. Power is the rate of change. The rate of doing work, the rate of work done, or work done over time taken, or work done per unit time. That is power. Rate of doing work, rate of work done. Then Young modulus, that is stress divided by strain. Stress divided by strain, that is Young modulus. Okay, a crane is used to lift heavy objects as shown in the figure here. So the mass is 1,800 and there is a motor at the other side. The motor in the crane lifts a total mass of 1,800 kilograms from rest. The cable supporting the mass is made of steel of Young modulus 2.4 exponent 11. The cross-sectional area of the cable is 1.3 exponent negative 4. As the mass leaves the ground, the strain in the cable is 0.001. Assume that the weight of the cable is negligible. Use the Young modulus of steel to show that the tension in the cable is that. So we know that Young modulus is equal to stress over strain. That will be equal to force over area. The strain is in the denominator, so it is times the strain. The force here is going to be equal to the tension. So the tension, I'm making you the force the subject, the tension is going to be equal to Young modulus times area times the strain. So we substitute. Young modulus is 2.4 times 10 power 11. The area is 1.3 times 10 power negative 4. And the strain is 0.001. 0. We can check by our calculator. 2.4 exponent 11 times 1.3 exponent negative 4 times 0.001. So that is 3.12 times 10 power 4, which is approximately 3.1 times 10 power 4 as required. Then calculate the acceleration of the mass as it is lifted from the ground. We need the resultant force. So resultant force equals to, it is mass times acceleration, but what is the resultant force? Let's check. So the weight is downwards and there's a tension in the cable upwards. The result is, since the mass is moving upwards, it means the tension upwards is greater than the weight. So the resultant force is upwards, so I will say tension minus weight. So this will be tension T minus the weight downwards, or which will be tension T minus the weight, which is M times G. So the mass was 1,800 times the acceleration equals the tension, which we have got at 3.12 times 10 power 4 minus the weight, which is mg, that is 1800 times 9.81. I'll just press my calculator. So that answer minus, open brackets, 1800 times 9.81. That is the answer. Divide by 1800 to get the acceleration at 7.52. So A is 7.52. The motor now lifts the mass through a height of 15 meters at a constant speed. Actually, the tension in the lift. If the speed is constant, it means there is no resultant force. Therefore, the tension equals to the weight. So it means the resultant force is 0, which is tension minus weight. That means the tension is equal to the weight. So it means the tension is going to be equal to the weight, which is mg. So that is 1,800 times 9.81. I've got this from the part of constant speed. At constant speed, acceleration is 0, resultant force is 0. The force upwards is equal to force downwards. So this is going to be 1,800 times 9.81, which is 1.8 times 10 power 4. 1.8 times 10 power 4 newtons. Then the gain in potential energy of the mass. So gain in potential energy is equal to mg times h. So m is 1,800, g is 9.81, 9.81, and they have told us H is 15. 1800 times 9.81 times 15. That is 2.64 times 10 power 5, I guess. 2.64 times 10 power 5. 2.64 times, is it 64? 65 times 10 power 5. So which is approximately 2.65 times 10 power 5. Lastly, for this video, part 2, the motor of the crane is 30% efficient. Calculate the input power to the motor required to lift the mass at a constant speed of that. So first of all, we need the power which is necessary. Power is equal to force times velocity. So the output power is, force is 1800 times 9.81. So the output power, the force is 1800 times 9.81, that is the weight. Then times the speed, which is 0.55. That is the output power. This is power out, or power that we need to output. So that is 1800 times 9.81 times 0.55. So this is 9711 or 9712 watts. That is the output power. But efficiency is equal to the power input, power out, over the power input. So efficiency is 30, so 30 over 100 is equal to power output, which is 9712, divided by the power input. So it means the input power, or power input, is going to be equal to, I just cross multiply, 9712 times 100 divided by 30. So that one times 100 divided by 30, that is 324. 3.24 times 10 power 4. So that is 3.24 times 10 power 4. Okay, let part 2 stop here. We shall complete this in part 3. I hope you enjoyed this. I hope you learned something from it. Thank you, and see you in part 3 of Work, Energy and Power.